Okay, everyone, let's begin with this then. So we are starting differentiation today. In the last few sessions, we have completed our trigonometry topic. At least in terms of concepts, we will be doing more practice on that tomorrow, inshallah, before which you are expected to have attempted all the assigned questions and more from recent past papers. But for today, we're moving on to our next topic so that over the weekend then, after tomorrow's class, you can do practice on differentiation as well, so that when we come back on Monday, we can do differentiation practice then. Okay. Now, in terms of concepts, differentiation is not something that takes a lot of time. So we will try to complete most of the concepts that we have in this topic today, because in terms of concepts, there isn't really a lot. Okay. But it does require a lot of practice. That is why if you're able to complete most of the concepts today, it will be helpful because you would have them 3-4 days to practice before we come back next week. And then we can attempt questions from the worksheet then. Okay, so let's start with this. Now, again, as with all the other P3 topics, the understanding is that you need to know the P1 concepts corresponding to that topic, right? So P1 differentiation, all the concepts from P1, you need to know them as well. So what are those concepts? In paper 1, you've done this power rule, right? X raised to power n. How do you differentiate that? N x raised to power n minus 1, multiply by the power, subtract 1 from the power. You've done this rule in paper 1. And you have done this general power rule as well. If you have anything raised to power n, what do? You multiply by the power, subtract 1 from the power, and then you also divide by the derivative of whatever is the base of the power, right? For instance, if you have an expression like this, how do you differentiate it? The constant that's multiplying outside, that remains as it is. And then you multiply by the power, minus 4/3. That's what is multiplying here. You subtract 1 from the power, so minus 4/3 minus 1, that gives you minus 7/3. And then you multiply by the derivative of the base. This is the base. You multiply by the derivative of that outside. X cubed, that becomes 3x squared, minus 4x, the derivative of that is minus 4. So you multiply by that derivative outside. This is as complicated as it could get in paper 1 as far as differentiating functions was concerned, but you need to be aware of this rule from paper 1, the power rule. Then there were different applications of differentiation. Different derivative is basically the gradient function. So inputting any value of x in the derivative, that gives you the gradient at that particular point. So if you have this derivative, you can input x equal to that value, whatever is the value at which you want to find the gradient, and you get the value of the gradient. That's one use of differentiation, that you can find gradients at a particular point. That's what you need to know from paper 1. And then remember those other concepts, the applications of differentiation, finding equations of tangents and normals, right? You will still need to do that in paper 3 as well, although not as frequently, but sometimes, yes, you need to do that. Equation of tangent, equation of normal. How do you do that? Equation of tangent, the gradient of the tangent is the same as the gradient of the curve at that point. So you find the gradient of the curve at that particular point using differentiation. And then you would have a point as well. And using that point and the gradient, you can then write down the equation of the tangent. For equation of normal, you find the gradient of the curve. Gradient of normal would be negative reciprocal of that. And then you use the point that is given to find the equation of normal using this form. And you can find that as well, right? This is something that you need to know from paper 1. Finding stationary points, the turning points of a function. How do you do that? For finding stationary points, you put dy/dx equal to 0, and that gives you the x coordinate of the turning point. Generally, to get the corresponding y coordinate, you can put that value back in the function to get the corresponding y coordinate. How do you figure out if a function, if a turning point is a maximum or a minimum? You find the second derivative for that. If the second derivative is positive, that's a minimum point. If the second derivative is negative, that's a maximum point. This is also something that you've done in paper one. Okay, so to find the turning points, you put derivative equal to 0. All right, and to figure out if the turning point is maximum or minimum, you use the second derivative. Negative second derivative means maximum point. Positive second derivative means minimum point. Okay, this will be done. This will be used very often in paper 3. You need to remember that. And then finally, the concept of increasing and decreasing functions. Increasing function is one in which the derivative is greater than 0. Decreasing function is one in which the derivative is less than 0. So if the derivative is positive, it's an increasing function. If the derivative is negative, it's a decreasing function. And then finally, chain rule, rate of change and chain rule. If you remember, you've also done this in paper one, although you don't get rate of change problems directly in paper 3. Generally, they don't test that, although they can, because anything in paper one, it can be tested in paper 3 as well. But generally, you don't get rate of change problems in paper 3. However, chain rule is something that you still have to use. Okay, chain rule is something that you still do have to use. Okay, so you need to remember chain rule as well. So yeah, these are all concepts that you need to know from paper 3. And now in paper 3, we will be doing some more advanced concepts than that. Okay. Yes, somebody else asked me about that as well. I think it was a hub. I will share that. I'll share some recordings and the notes of both the topics, differentiation and integration. Differentiation and trigonometry for now, and then integration as well. Before we start that, I will do that. I'll try to do that by tonight. If I don't do that, please leave me a reminder in the group as well, and you will get that in the group. Okay, I'll share the recordings and the notes in the group for these topics. Okay. All right. So in paper one, then we learned how to differentiate functions of this form when you have something raised to power n, so the power functions, right? We learned how to differentiate them using the power rule. That was just one rule that we did in paper one, essentially. And the rest of it was just applications of differentiation, right? Finding equations of tangents and normals, finding stationary points and their nature, increasing and decreasing function, rate of change and chain rule. In paper 3, we will still need to use all of those different applications of differentiation. But the new thing here is that we will learn how to differentiate a number of other types of functions now. Okay, a number of other types of functions, we will learn how to differentiate them. In paper one, we just did one type of function. Now we'll have a number of other types of functions. Now, we will do that first using what is given in the formula sheet. So I've taken this from the formula sheet. Okay. Now we'll go through these rules one by one from this. In paper one, you've just done this. X raised to power n. Derivative of that is nx raised to power n minus 1. That's what you've done in paper one. Now, the generalized version of this rule was that if we have anything raised to power n, so let me write that on the side, f of x and f dash of x, the formula sheet just tells you this. X raised to power n, derivative of that is nx raised to power n minus 1. That's all that the formula sheet tells you. Okay. You can generalize it like this, as we did in paper one, that if we have anything raised to power n, the derivative of that is going to be n, you multiply by the power, and then whatever that is, the power gets subtracted by 1, so n minus 1. But then there's one additional step that the formula sheet does not explicitly tell you. If you have anything other than x, any other expression, you also have to multiply by the derivative of that thing. Okay, whatever is inside the bracket, you also have to multiply by the derivative of that thing outside. So if you have, for instance, using a simple example, let's say you have 2x plus 1 whole raised to power minus 3, and you want to differentiate it, the derivative would be minus 3 multiplied 2x plus 1, subtract 1 from the power minus 3 minus 1, that becomes minus 4. And then you multiply with the derivative of this part, 2x plus 1, which is 2, you also multiply by that. Okay. When there was just x there as the base, what's the derivative of x? Derivative of x is 1, right? So here as well, the derivative was multiplying, but it's not visible because multiplication by 1 does not really change anything, right? So it's just multiplying by 1 here. So in case of x, we don't show that explicitly that something is multiplying. But if it's anything other than x, like this, we need to make sure that we also multiply by the derivative of that. In case of x, the derivative is just 1. So that's why it's not visible there. Okay, for any other thing, it will be explicitly multiplied on the side. All right, so that was the power rule that we did. Now we have a number of these other rules that we need to also know about. Let's start with these rules one by one. So it says ln of x, we have done logs, right? Just to confirm, yeah. So ln of x, derivative of ln x is 1 over x. That's what the formula sheet says. Okay, if you have ln of x function, its derivative is going to be 1 over x. Now again, you can generalize that. You can say, okay, derivative of ln x is 1 over x. What if we have ln of anything else? Any expression in terms of x, what if you have to find this? What is this going to be? You apply that rule as it is, 1 over x. So essentially, whatever comes in place of x, whatever comes in place of x, what happens to that? That goes to the denominator like this, and you have 1 over that thing. Okay, but then you also have to multiply by the derivative of that. You multiply by that. Multiply the derivative of that thing. Let's take an example. Let's say you have a function that looks like this: y equals ln of x squared plus 2. And you want to differentiate it. You want to find the derivative of this. Now, what does the rule say? Whatever is inside the bracket here, that is going to go to the denominator. Okay, so it becomes 1 over that thing, which is x squared plus 2. Right? That's how the rule works. And then whatever this thing is, you multiply by the derivative of that. What's the derivative of x squared plus 2? It's 2x. You multiply by that, and the result therefore turns out to be 2x divided by x squared plus 2. That's the answer that you get from this. That's the derivative of ln of x squared plus 2. Make sense? Let's take another example. Let's look at the next rule now. Derivative of, so just look at one function at a time. Okay, don't look at the whole thing in case that's scaring you. Okay, it's just one function at a time. So what I'll do is let me see if that's gonna work. So I'll just get rid of this somehow. But it's, don't look at the other functions for now. Okay, one function at a time. Can't do that. You get my point, right? Let's look at the next function now. Don't look at the others for now. Just e power x. Derivative of e power x is e power x. It remains as it is. Okay. Now, how do we generalize this? If we have e raised to power anything else, what's the derivative of that going to be? It's going to be the same thing again. E power that thing, it does not change. However, whatever is coming in place of x, you have to multiply by the derivative of that as well. So you have this multiplying on the side. Okay, so what am I representing this box by? As in, what does this box represent? This represents any expression in terms of x, right? So this box can be filled by anything in terms of x. And then what about this box dash? That is the derivative of that. Okay. So in case of this box, you could have any expression in terms of x. That's what we mean by that. And then box derivative. What does that mean? Derivative of whatever that thing is. Let's take an example of this now. Let's say you have e raised to power 3x. And you want to find the derivative of this. What would this be? dy over dx. That is going to be e raised to power 3x as it is. Okay. And then the derivative of 3x, what's that? That is 3. And that simplifies to 3e raised to power 3x. Okay? That's the derivative that we get from this. Any logic behind these differentiations? Well, all of these differentiations, they actually come from this idea that we study in paper 1, although it's not part of syllabus as such, but this idea. So this is part of syllabus when you draw these chords in paper 1, if you remember, and then looking at the pattern of those chords, you arrive at the derivative. So it comes from this process. It's called differentiation by first principles. We prove this for x squared generally in paper 1, just to get a feel of it. So this is the same process using which you find all of these derivatives, but it's beyond the scope of our syllabus and this class right now. They're all given in the formula sheet. We will just be using them. Okay. All right, but it comes from that first principles thing that we study in paper 1. All of these are derived from there, but it also involves the concept of limits that you do not know about yet. You will study that in your first math course at university, calculus. But for now, we'll just believe that these are the derivatives. Okay. All right. So e power x remains e power x, but in case x is replaced with anything else, we just have to make sure we also multiply by the derivative of that. Okay. Derivative of sine. Derivative of sine x is cos x. Okay. Derivative of sine is cos. If you want to generalize this, it becomes that the derivative of sine of anything, that is cos of that thing, multiply by the derivative of that, right? It's the same pattern that is going to be there with all of these functions now. So I'm going to write down the rest of them quickly now. So derivative of sine is cos, and then the derivative of cos of something, that is minus sine of that thing into derivative of whatever is inside this bracket. So whatever x is replaced by, you have to multiply by the derivative of that as well. Okay, so that's what's happening in all of these rules, right? So if you have tan of anything, the derivative of that is secant square of that multiplied by the derivative of that thing. Let's take an example now of, let's say, tan. If you had y equals minus 3 tan of, let's say, x cubed minus 4, what would be the derivative of that? The rule says the derivative of tan of something is secant square of that thing, right? So its derivative is going to be dy over dx. Remember, when we have something multiplying outside, that remains as it is. So minus 3 is going to remain as it is. That does not change. Tan of this thing, what does that become? That becomes secant square of that thing. So we have secant square of x cube minus 4. But then whatever is coming in place of this box, we also have to multiply by the derivative of that. What's the derivative of x cubed minus 4? That is 3x squared. We have to multiply by that, and that's the result that we get. That's the derivative. We can simplify this if we want. 3x squared and minus 3, they can get multiplied and give us minus 9x squared times secant square of x cubed minus 4. You can't multiply x cubed minus 4 with anything because that is the angle inside secant square. Okay, so no multiplication can be done with that because secant square is applying on that. So this is the final answer that you get. This is the derivative of minus 3 tan of x cubed minus 4. Okay, I'll pause here for a few seconds to allow you to digest this. Let me know if there's any problem until this point. Are these rules clear to everyone? Any problems? Okay. All right, good. Now, these are all given in the formula sheet, although you will start remembering them as you practice, and you should start remembering them. Now, don't try to, again, sit down and start rote learning. That's not the way it works. You will just do a lot of practice, and you would realize that you will start remembering most of these rules automatically. But you still have the formula sheet as a backup, right? You can use that. Let's look at the next one now. Derivative of secant x is secant x tan x. Again, if x is replaced with anything else here, what is this going to become? It becomes secant of anything. The derivative of that is secant of that thing into tan of that thing, right? This is what it says. But then you also have to multiply by the derivative of whatever is inside the bracket there. You multiply by the derivative of that. Similarly, if you have cosecant of anything, the derivative of that would be given by minus cosecant of that thing into cot of that thing into derivative of whatever is inside the brackets there, whatever is x replaced with. Okay, then we have cot of anything. Derivative of that is given by minus cosecant square of that thing into derivative of that. And then finally, if we have tan inverse of anything, what does the rule say? 1 over 1 plus x squared. So again, you have x here and you have x here. So whatever comes in place of x, you write it in that same place where x is in this case. So it becomes 1 over 1 plus that box whole squared. And then, as with all the other rules, you multiply by the derivative of this, like this. These are all the rules that we will have for differentiation in cases when we can differentiate the function directly. Okay, now there will be cases where we will not be able to differentiate directly. We'll have to do something else. But when the function can be differentiated directly, this is how we apply all of these rules. Okay, now I'll do some more examples of the last few ones because we did not do any of them. We did not do examples of them. So let me do some for the last few functions. Let's say you have a function that looks like this. Y equals cosecant of 3x squared. I want all of you to write down the derivative of this. You've got the formula sheet. The only thing that you have to add yourself is that you multiply with the derivative of whatever is replaced, whatever x is replaced with. Yeah, what's the derivative of this? What do we get? Derivative of cosecant is minus cosecant times cot. Let's write that down. dy over dx. What is that going to be? Minus cosecant, so we're using this rule. Minus cosecant times 3x squared times cot of x. So that means cot of 3x squared times the derivative of this thing. What's the derivative of 3x squared? That is 6 times x. And now we can simplify this if we want, but that's the rule. That's how it works. That's the derivative of cosecant 3x squared. Let's do another one. Let's say we have y equals minus 5 over 7 times tan inverse of 2x plus 1. What's the derivative of this now? Again, can all of you try this now? I'll give you a minute to do this. Please write in the chat quickly the answers that you get. I want responses from every one of you, please. Remember the constant that's multiplying or dividing outside, that remains as it is, right? So minus 5 over 7, that will remain as it is. The rule is only going to apply on this thing. And this is the rule that we have, tan inverse. Remember, it's tan inverse, not tan. Yeah, so let's do this. dy over dx minus 5 over 7, that remains as it is. Okay. And then let's apply this rule. 1 over 1 plus x squared. So whatever is x replaced with, you have that thing here. That's 2x plus 1. So you multiply by 2x plus 1, and then whole squared of that, times the derivative of this thing. What's that? That is 2. This is what we get. We can simplify this if we want, because that gives us minus 10 over 7. And then in the denominator, we have 1 plus 2x plus 1 whole squared. You can leave it like this. It depends on what you want after this in the question. But that's the derivative, and that's how the process will work. This is what we get. Yeah, so if you want to simplify the denominator further, you can do that. That will depend on the question, what they're asking for after the step. You can do that as well. All right. Okay, let's take another example now. Now let's say we have something like this. Y equals minus 5 sine of 2x plus 1 whole squared. How do you find the derivative of this now? Minus 5 sine of 2x plus 1 whole squared. What's dy over dx for this? Okay, minus 5 is a constant that remains outside as it is. What's the derivative of sine? Derivative of sine is cos, right? So this will convert to cos. Let me actually show you the formula sheet in front of you as well. Yeah, so that's the one on top here. Okay, anyway, so you have that on top. Derivative of sine x is cos x, right? Let's use that. This is going to become cos of 2x plus 1 whole squared. Okay? But then we also have to multiply by the derivative of this thing. What's the derivative of this thing now? To differentiate this, you would have to use the power rule now, right? Because this is a power function, 2x plus 1 whole squared. Let's differentiate this thing now. Multiply by 2. Subtract 1 from the power. So you multiply by the power, subtract 1 from the power, 2 times 2x plus 1 power 1. And then you multiply by the derivative of the base of the power, and that will be 2 here. That's the result that you get from this. Okay, this is a more complicated one. It's one function inside another function. So sine was the outer function. You apply the rule of the outer function first. Sine is the outer function in this case, right? So what's the rule for sine? Derivative of sine is cos. Okay, so you start from that and you say, okay, it becomes cos of this. But then this is the expression inside sine. You have to multiply by the derivative of this. What's the derivative of 2x plus 1 whole squared? That's 2 times 2x plus 1 times 2 outside. Now you can simplify this and see what that gives you. Minus 5 times 2 times 2, that will be minus 20. And then this expression, that's 2x plus 1 times cos of 2x plus 1 whole squared. If you want, you can simplify this further, or you can leave it like this, but that's how the rule works. Is that okay? Let's take another example. Let's say you have y equals ln of x raised to the power 5. What about this now? Derivative of this. What's this going to be? Derivative of ln. So that's the rule on top. Let me just write it here. The rule that's given in the formula sheet is like this. Derivative of ln x is 1 over x. That's what the formula sheet says. Okay. Now, how do you use that rule? This is the expression that is replacing x, right? So you say it's 1 over x raised to the power 5. Okay. But then you have to multiply by the derivative of this as well, right? This is the thing that you have here. You multiply by the derivative of this. What's that going to be? Derivative of x raised to the power 5 is 5x raised to the power 4. You can do some simplification here now. X power 4 and x power 5, they get cancelled. You're just left with power 1 here. That becomes 5 over x, and that's the derivative, 5 over x. Okay. Another way to do this could be that you apply the power law of logs first, right? That will make it simpler so that the function becomes 5 ln x, right? So you could write the function as 5 ln x. And then the derivative of that would just be 5 times 1 over x. That's 5 over x. That could be another way of thinking about this if you first use the power law before differentiating that. Make sense? Now, what if instead of this, you wanted to differentiate y equals ln of x whole power 5? Notice the difference. You have ln x raised to the power 5 in the previous example. Now we have ln x whole raised to the power 5. What about this now? How do you differentiate this? Now, in this case, you see the outer function is the power function. In the previous case, it was the log function. Now, in this case, the outer function is the power function. So the rule that is going to apply here is going to be the power rule, right? So what's the power rule? This one. That's the rule that applies. So when you differentiate a function in which you have one function inside another function, you start differentiating from the outermost function. Okay? What's the outermost function in this case? The outermost function in this particular example is the power function, right? So you apply the power rule on this. What does the power rule say? You multiply by the power, subtract 1 from the power, so it becomes 5 times ln of x power 5 minus 1, which is 4, multiplied by the derivative of the base of the power. What's the derivative of ln x? That's 1 over x. And that's the derivative that we get. We can simplify this to get 5 over x times ln x whole raised to the power 4. That's the derivative that we get in this case. We would need to use power rule here. Okay, because that's the outer function. The power function is the outer function. Let's take another example. Let's say you have y equals ln of cos of 2x. How do you differentiate this now? Y equals ln of cos of 2x. What's the outer function in this case? The outer function is the log function, the ln function. What's the rule for ln? Okay, but by the way, I would recommend that you take a printout of the formula sheet. If you haven't done that yet, please do that. You will need to have that in front of you for trigonometry questions, for differentiation questions, for integration questions. Please print that out and have that in front whenever you're doing all of these problems, any of these problems. ln of cos of 2x. What's the outer function? The outer function is log here. So the rule that will apply on this first is going to be of the log function. What does that say? Derivative of ln x is 1 over x, right? That's what is given in the formula sheet. Okay, so what does this become then? dy over dx. 1 over cos of 2x. 1 over cos of 2x. Make sense? Multiplied by the derivative of cos of 2x, which is derivative of cos is given to be minus
sin 2x.
Yeah, so in the formula sheet, it says derivative of cos x is minus sin x, right? That's what the formula sheet says. But now in this case, you have cos of 2x. So the derivative of that would be minus sine of 2x. Is that it? Is that going to be the derivative of cos 2x? Or do we do something else as well?
Multiply by 2.
Multiply by 2, because that's the derivative of 2x. The rule says that you also have to multiply by the derivative of this expression. It's not x, it's 2x now. You have to multiply by that. So we multiply by 2. Okay. So we had cos of 2x here. We multiplied by the derivative of that. That gave us minus sine 2x. But we also had to multiply by the derivative of that, which is 2. That's the result that we get from this. We can simplify this further if we want, but that's the final result. Okay?
Sir, I have a question.
Yes.
Sir, can you show the process to simplify, like this expression? What should I do first to simplify it? Like break down.
After this?
Yes, after this.
Okay. You have this number multiplying. You can write that here. And you have this negative sign as well. You can write it like this. First of all, minus 2 sine 2x divided by cos 2x. Does that not make sense until this point?
Yes.
And then, if you want, you can write sine 2x over cos 2x as tan 2x as well. So this is how far you can simplify it if you need to. Minus 2 tan 2x. That's the derivative of this thing that we're getting. Okay. But that will depend on what they require in the question. If they want you to convert something to tan, you would do that. Yes, Ibrahim?
अस्सलामुअलैकुम सर।
Right,
सर मेरा
Mas.
कनेक्शन पास हो गया था, ये आप दोबारा बता सकते हैं कि जब आपने 1/cos 2x लिया
Hmm.
तो x तो cos 2x है, अब x का ही हमने डेरिवेटिव लेना है आगे, तो वो -sin 2x हो जाएगा, तो फिर ये आगे वाला 2 किधर से आया?
What's okay? So the question is, we have cos 2x here, and now we have to multiply with the derivative of this, which is minus sin 2x. Where is this 2 coming from? We have cos of 2x here, right? Cos 2x. What's the derivative of cos 2x? We apply the rule. Cos 2x becomes minus sin 2x. But what does that rule say? If you have anything except x here, you would have to multiply by the derivative of that. What's the derivative of 2x? It's 2. So you also have to multiply by 2. So the derivative of cos 2x is actually this whole thing. Right? This 2 is part of the derivative. Make sense?
और सर, थैंक यू सो मच।
All right, one last example before we move on to the next thing. Let's say we have something like this. This is an important one. If we have sine squared of 2x, or we can use another number, let's say 4x plus 3. We want to find the derivative of this, dy/dx. How do we do this now? Sine square of 4x plus 3. What's the outer function? Is power the outer function or sine the outer function?
Sine.
Sine or power? Sine. Remember, this is just a short way of writing. We discussed this earlier in trigonometry. The actual mathematical function is sine of 4x plus 3 whole squared. This is the proper mathematical way of writing that. This thing is just a short form for that, right? The actual thing is sine of 4x plus 3 whole squared, like this. Okay? So if you notice here, the outer thing is the power function. So now if you differentiate it, it's going to look like this, dy/dx. Apply the power rule on this. You multiply by the power, 2 gets multiplied here. Subtract 1 from the power, so you have sine of 4x plus 3 whole power 1, 2 minus 1, right? That becomes 1, multiplied by the derivative of this thing now, right? Derivative of the base of the power. What's the derivative of sine? Derivative of sine is cos. It's right here. Derivative of sine is cos. So now we apply the rule for sine. What's the derivative of sine? It's cos. So we multiply outside by cos of 4x plus 3. But then we also have to multiply with the derivative of this, which is 4. This whole thing is the derivative of sine of 4x plus 3. We're multiplying with that. And now we can simplify this if we want. That will give us 2 times this 4, that's 8, times sine of 4x plus 3 times cos of 4x plus 3. That's the derivative that we're getting in this case. Does this make sense to everyone? This is as complicated as it could get as far as a function inside another function is concerned. So whenever you have something like this, what you do is you start differentiating from the outermost function. Okay? Yes, Saad.
सर मैं फिर इस चीज में कंफ्यूज हो रहा हूँ, जो आपने एंड में जो सिंप्लीफाई किए हैं ना, इस चीज में फिर मैं कंफ्यूज हूँ। जैसे पहले हम लोगों ने जो किया था उस तरह आपने नहीं किया, थोड़ा कंफ्यूज हो गया।
Remember, when we do simplification, we can only multiply or divide the expressions that are outside sine cos tan, right? The only thing that we have outside sine cos tan is this 2 and this 4. right? We can't do anything with this 4x plus 3 and this 4x plus 3. They're inside sine, inside cos, right? We can't multiply them outside with anything. So we're just multiplying 2 and 4. In the previous case, we just had 2 outside. So we just wrote that 2 here. And that's it. Everything else remained as it is. Sine 2x over cos 2x. So what's the problem? Where is the confusion? Saad?
सर इसी चीज को कंफ्यूज हो रहा था कि पहले हम लोगों ने किया था तो -2 था, इस दफा मैं कर रहा था तो मेरा आंसर थोड़ा चेंज हो रहा था, इस वजह से मैं कंफ्यूज हो गया था। अब समझ आ गया।
Okay, good. All right. So whenever you have one function inside another function, you start differentiating from the outermost function. Okay. So that's one thing that you need to remember. All right. Now, this is how we integrate functions that look like this. Okay. Where you can apply one of these rules directly. But then, what if you have multiple functions? Let's say you have something like this. First of all, y equals x squared plus sine x, for instance. How do you differentiate it? Y equals x squared plus sine x. You can differentiate each term separately, right? This can be differentiated as derivative of x squared. What's that? That's just going to be 2x. Derivative of sine x. What's that? That is cos x. So dy over dx turns out to be 2x plus cos x in this case. Okay. Now that's fairly straightforward, finding the derivative of this. But now, what if we had dy over dx equal to x squared times sine x? What about this? How do you differentiate this function now? X squared times sine x. So x squared and sine x, they're multiplying now. What's the derivative of x squared? That is 2x. Derivative of sine x, cos x. This is not going to work. Okay. In the previous example, they were separate terms. X squared was a different term. Sine x was a different term. So we could differentiate each one of them separately. X squared could be differentiated separately. Cos sine x could be differentiated separately, and we got the derivative, and that was correct. But when they're multiplying, this whole thing is one single term. Right? This whole thing is one single term. We can't say that we just multiply the first term this expression separately and this separately. It does not work like that. Okay. When there's a product, you cannot do it like this. That does not work. So what do we do instead? We use something that we call the product rule. Okay. Product rule of differentiation. That is what we will be using to differentiate this now. Okay, product rule of differentiation. Now, what does the product rule say? This is what it looks like. So in the formula sheet, it will be given in this form. Y equals u times v. If we have a function of this form, y equals u times v, where you have two expressions multiplying, the derivative of that dy over dx, that is equal to u times dv over dx plus v times du over dx. Okay, it's written like this in the formula sheet. U into dv over dx plus v into du over dx. Okay, a short way of writing this and remembering this is that we write it like this: y equals uv. If that's the function, then the derivative of that dy over dx, that is uv dash plus vu dash. Okay, so dash means the derivative. uv dash plus vu dash, that's the product rule of differentiation. Now, what are u and v here? U and v are any expressions in terms of x. u and v are any expressions in terms of x. Okay, let's take an example. So we looked at this function earlier. Okay, I'm sorry, this was y, not dy over dx. Y equals x square times sine x. And we cannot differentiate it like this. So how do we actually differentiate it then? Y equals x squared times sine x. That's the function. We have two things multiplying, two functions multiplying here. Okay. What we do is we call one of them u and the other v. So in this case, for instance, we can say, let's say this is u and this is v. What is the derivative going to be? Dy over dx. Dy over dx is going to be uv dash plus vu dash. Right? It's going to be uv dash plus vu dash. That's what the derivative is going to be. Now, the first few times you do it, you can evaluate them separately and then input them there. And then once you have done some practice, you'll be able to do it directly as well. Let me do it separately for now. So I'm saying this is u and this is v. Okay. So u is equal to x squared. Let me just write that separately here. And v is equal to sine x. What's the derivative of u? U dash, that is 2x. Derivative of v dash is cos x. Right? Derivative of sine is cos. So v dash is cos x. All we have to do now is input these values in this formula. uv dash plus vu dash. U is x squared times v dash, that is cos x, plus v, which is sine x, times u dash, which is 2x. And that's the result that you get. This is the derivative of that function, x squared times cos x plus 2x times sine x. This is dy over dx for this function. All right. Make sense to everyone? Let's take another example. Let's say instead of this, we had y equal to e raised to power 2x times ln of x or 4x. Okay, now we have this function. Again, two things multiplying. We cannot differentiate it separately. We have to do it all together. What do we do for that? We use the product rule. What does the product rule say? We have two expressions. Let's call one of them u and the other v. Okay, and now dy over dx, what is that going to be? U v dash plus vu dash. That's what the derivative is going to be. Dy over dx equals u, which is e power 2x. Or you can actually write it on the side first. U equals e power 2x and v equals ln of 4x. Let's find the derivatives. What's u dash? E power 2x times 2. So that becomes 2e power 2x. Okay, now what about v dash? That is 1 over 4x times derivative of 4x, which is 4, and that simplifies to 1 over x. So u dash is this and v dash is this. All we have to do now is input these values in the product rule, and that will give us the derivative. dy over dx equals e power 2x times v dash, which is 1 over x, plus vu dash, v is ln of 4x, times u dash, which is 2e raised to power 2x. And now we can simplify this which gives us e raised to the power 2x divided by x plus 2e raised to the power 2x times ln of 4x. That's the result that we get from this.
Sir,
Yes.
sir, isn't ln 4x? So it would be 1 upon 4x?
Yeah, but 4 and 4 are getting cancelled, right? Which 4 are you talking about?
Yeah, I get it.
Okay, that's the derivative in this case. That's how the product rule works. All right. Then what happens if we have a division? If one thing is being divided by another thing, we use a rule that's called the quotient rule. For that quotient rule, let's think about this now. If we have a fraction like this, y equals, let's say, tan of 2x divided by x squared. Okay, so we have this fraction now. Again, we have two things dividing. We cannot differentiate them separately. We'll have to do it all together. For expressions like these, we use a rule that's called the quotient rule. And we use that when we have one thing divided by another thing. What does that rule say now? In the formula sheet, it's written like this. If you have y equals u over v, the derivative of that is given by v into du over dx minus u into dv over dx divided by v squared. Okay, that's what the formula sheet says. Another way to write that same thing would be that if we have y equals u over v, the derivative of that is vu dash minus uv dash divided by v squared. Okay, it's the same thing. Instead of the derivative written like this, du over dx, I'm just writing that as u dash. And dv over dx, I'm writing that as v dash. That's called the quotient rule. Okay, and we use that when we have one thing divided by another thing. So in this case, for instance, how is this going to work? We call one of them u. Let's say this is u and this is v. We apply the quotient rule now. Dy over dx. What is that equal to? This is what the quotient rule says. Vu dash minus uv dash divided by v squared. Let's evaluate them separately. U is equal to tan of 2x and v is equal to x squared. What's the derivative of tan? You can look at the formula sheet. Derivative of tan is secant squared. Okay. Derivative of tan is secant squared. So u dash becomes secant square of 2x multiplied by 2. We have to multiply with the derivative of 2x, right? And then v dash is 2 times x. And now all we have to do is input those values in this, and we'll get the result. V is x squared times u dash, which is this whole thing, minus u, which is tan of 2x, times v dash, which is 2x, divided by v squared. So x squared squared, that becomes x raised to the power 4. That's the derivative that we get. If we want, we can simplify this a bit. 2x squared secant squared 2x minus 2x into tan of 2x. Remember, this 2x is inside tan. We cannot multiply that with this 2x. That's outside tan. In the denominator, we have x raised to power 4. If we want, we can take x common from the numerator to simplify this. But that's just simplification, right? The differentiation process is just until this point. If you take x common from the numerator, you can write this as 2x into secant squared of 2x minus 2 tan of 2x. So I'm taking this x and this x common. 1 power of the first x and the second x. And now we can cancel this out with 1 power of the denominator if we want. And that gives us 2x secant squared 2x minus 2 tan of 2x divided by 3. That's the derivative that we were looking for. Okay, so this is how this differentiation process works. Any questions on this, anyone? Any questions on this?
Sir, while solving a problem, we don't really need to write the formula like
No.
you.
That's just for your own ease, just to make sure that you're not doing any careless errors. Otherwise, it's not necessary to write this. It's not necessary to write this. You can start with this as well. But that comes with practice. Once you've done some practice, you'll be able to do it directly, yes. It would be x cube. Yeah, x cube. I wrote this 3 there in the denominator. Oh, x cube, sorry. All right, so what we've done is how to differentiate all of these different types of functions using these rules. Just remember, in the formula sheet rule, you just have to multiply with the derivative of whatever comes in place of x as well. And then we did the product rule of differentiation and the quotient rule of differentiation, okay? One last thing, there are 2 more things that we are left with in terms of differentiating functions. And then there's some more detail after that. We can't do all of that today. Implicit differentiation is the relatively more complicated thing. I will leave that for the next class now, because otherwise a lot of you end up leaving at this point. So what I'll do is I will cover parametric differentiation today. We'll have a look at one example after that, and then we end for today. Implicit differentiation, that is what will be left for the next class then. So apart from that, you should be able to do the rest of the questions then for the next class. But this is important. I want to do this parametric differentiation so that you are able to attempt like 50% of the worksheet at least, or more than 50%. So everything apart from implicit differentiation, you should be able to do it after this. So that's why I want to cover this, so that over the weekend then you can do a number of questions from the worksheet. Otherwise, then next week, there won't be enough time to do all of that. Okay, so there are 2 other types. There are 2 other methods that we have to do. One is parametric differentiation, and another is implicit differentiation. Now, we're starting with parametric differentiation. It's pretty straightforward. And it works like this. The idea is sometimes you have a function defined using 2 equations. Okay. So let's say you have a function like this that is defined in terms of 2 equations. Y equals 2 sine of t, and x equals t squared plus 5t. Okay. Y equals this and x equals this. These equations are known as parametric equations. Okay. These equations are known as parametric equations. Let me just write that down as well. These equations are known as parametric equations. What are parametric equations? These are equations in which x and y are defined in terms of a third variable. Okay. X and y, they are defined in terms of a third variable. And this third variable, we also call this parameter. Okay, which in this case is t, right? Parameter is just another name for variable, but there's a slight difference, which is not significant for our purposes for now. But it's just another name for variable, basically. Okay, so this third variable that we have, t, we call this a parameter. Okay, so when you have a function defined in terms of two equations like this, we call these equations parametric equations. And from these equations, if we had to find out dy over dx, this differentiation process is known as parametric differentiation. Okay. Now think about this. This should remind you of something that we've done in paper 1. If we have y equal to this, x equal to this, and you want to find dy over dx, you have three variables. How do you connect three variables using differentiation? You use the chain rule for that, right? That's what we can use here. We have two functions. One is, we have two equations. One is y equals 2 sine t, and the other equation is x equals t squared plus 5t. What we want to find is dy over dx. Now, one idea could be that you try to make t the subject from one equation and then put that in the other equation, and then, so basically eliminate t from one equation, put that in the other, so that you have an equation in terms of y and x. That's one idea, but that makes things very complicated. You generally would be required to find dy over dx in terms of t in such cases. So the variable should be t in the final form that you get. Now, how do you find that? These are the two equations that you have. You just differentiate each one of them separately. So you differentiate this first. What does that give you? Dy over dt. Remember, the derivative here is t, right? Instead of x, we have t. So when we find the derivative, it's going to be dy over dt. What's that? 2 remains as it is. Derivative of sine is cos, so it becomes 2 cos of t. And then here, we have x equals t squared plus 5t. When we find the derivative of this, that's going to be dx over dt. Okay? What's that? Apply power rule on this. That's 2t plus 5t. Derivative of that is 5. You have dx over dt equal to this now. Is that okay? Now, once you have dy over dt and dx over dt, what you're looking for is dy over dx. How do you do that? You can use chain rule for that. You would say dy over dx, that is equal to the product of two fractions. Okay. And what are those two fractions? We write it like this. This numerator is going to be the numerator of the first fraction. This denominator is going to be the denominator of the second fraction. Okay. That's how you write the chain rule. Numerator of the first fraction is going to come from here. Denominator of the second fraction is going to come from here. And then in the remaining places that you have, these two places, you have whatever is the third variable. What's the third variable in this case? It's t. So you would have dt here and dt here. And now you just have to input values. Dy over dt, what's that? That's 2 cos t. Let's input that here. 2 cos of t. And then dt over dx, what would that be? Reciprocal of
1
this.
upon 2t.
Just input that now. 1 over 2t plus 5, reciprocal of that. And the result, therefore, dy over dx turns out to be this. It's 2 cos t divided by 2t plus 5. That's the derivative that we're getting here. This is called parametric differentiation. When you have a function given in terms of two equations, you can find the derivative using this method. Is that okay? Now, I'll just leave you with one example. Okay, just one quick example on parametric differentiation, and then you can do more practice yourself. Just skip the implicit differentiation questions. Apart from that, you should be able to do everything else from the worksheet. At least you should be able to attempt all of the questions. And then the problems that you have, we will be discussing them next week. Let's just do one quick question and then we end for today. This will be the worksheet that you will see uploaded by tonight, inshallah. P3 differentiation. Okay, I'll just do one quick question on parametric differentiation and then we end for today. We have these parametric equations of a curve. And in the first part, they want us to find dy by dx in terms of t. Okay. These are parametric equations, x equals this and y equals this. What they want us to do is find dy by dx in terms of t. Let's try that. Part one. One equation is x equals ln of tan t. And the other equation is y equals sine square t. How do we differentiate the first one? Which rule is going to apply? Which rule is going to apply? The ln rule, right? Because ln is the outer function. What's the rule for ln x function? It's written in the formula sheet. Derivative of ln x is 1 over x. Okay, you can have a look at that. If we apply that rule here, dx over dt, it becomes 1 over tan of t. But then you have to multiply by the derivative of this thing. What's that going to be? Derivative of tan is secant squared. Okay, again, written in the formula sheet. The formula sheet says tan x, derivative of that is secant square. So this becomes, this gets multiplied by secant square t. That's what we're getting. Secant square t over tan t. This is dx over dt. Okay, let's find dy over dt. How do you differentiate this quickly? And can anyone tell me, how do you differentiate this?
Yes, sir, whole will be square.
It will be sine t whole squared, right? So we first of all write it like this. It's sine t whole squared. So we apply the power rule on this, right? We can't write it as cos squared t. That's not going to be correct. It's the power function outside. So we have to apply the power rule on this. What does that rule say? Multiply by the power. So dy over dt, that is equal to 2 times sine of t, subtract 1 from the power, so it becomes power of 1. And then you multiply with the derivative of the base of the power, derivative of sine t. What's that? That is cos t. That's what you multiply here. And the result turns out to be 2 sine t cos t. That's what we were looking for. We have dx over dt and dy over dt. Now, we need to find dy over dx. So we use the chain rule now. Dy over dx, that equals dy is the numerator of the first fraction. Dt will be the denominator of the second fraction. Sorry, dx will be the denominator of the second fraction. And in the remaining places, we have the third variable, which is dt and dt. Dy over dt, that's this. 2 sine t cos t multiplied by dt over dx, that's reciprocal of this, tan of t divided by secant square of t. This is what we're getting when we simplify, when we find dy over dx using chain rule. Can we simplify this further in any way? Because that might be helpful for the next part if we do that. Let's see if we can simplify this. What is secant squared? Secant is reciprocal of cos. So we could well write it as, let me actually do it on the side for you. denominator has secant square, right? So that will become 1 over cos square, right? In the denominator. I can bring that cos to the numerator then. Or maybe I will do it step by step for you here, because I have to change tan as well. Tan can be written as sine t over cos t, right? And secant square can be written as 1 over cos square t, right? Okay, now let's simplify this further. It becomes 2 sine t cos of t. In the numerator, we have sine of t. We can cancel out 1 power of cos with this, and 1 cos goes to the numerator, and we have another cos here. This is what we get, which simplifies to 2 sine square t cos square t. This is what we are getting as dy over dx. Any problems with this? Any problems with the first part? No problems? Okay, let's look at the second part now. The second part says find the equation of the tangent to the curve at the point where x is equal to 0. Equation of tangent. Tangent is a straight line. We need two things for that, a point and gradient, right? We need a point on the line and the gradient of that line. Gradient is going to come from the derivative, right? But how do you find a point? We have x equal to 0 given. We can find the corresponding value of y to get the point. Okay, now how do we do this? Let's find the point first of all. X equals 0, that's all that we know, right? How do you find the corresponding value of y from this? X is in this equation. We would have to input x equal to 0 here, right? We would input x equal to 0. That will give us the corresponding value for t. Once we have that value of t, we would input that value of t in the other function, and that would give us the corresponding value for y. Okay, so it's going to be quite a few steps in order to get to that point, point's y coordinate. The function is written like this: x equals ln of tan t. Let me write that here. And y equals sine square t. The point that we are given is x equal to 0. Let's input x equal to 0 here. What does that give us? 0 equals ln of tan t. Okay, now ln goes to the other side. Remember what happens when ln goes to the other side? It becomes the base of that number in power form. So it becomes e raised to power 0, right? When this goes to the other side, it becomes e power 0. And on the right side, we have tan t left. Right? E is going to the other side, becoming the base of 0. Okay, so e power 0 equals tan of t. What's e power 0? E power 0 is 1. 1 equals tan t. Find tan inverse of 1. Remember, you always use radians here. Never use degrees. Always use radians. The value of t turns out to be pi over 4 for this. You put this value there in the other function. Y equals sine square t. What does that mean? Sine t whole squared. So that's sine of pi over 4 whole squared. Put this on your calculator. See what you get. Sine pi over 4. Your calculator is going to give you square root of 2 over 2 for that. And then you square that. That becomes 1 over 2. 2 over 4, that's 1 over 2, right? Y equals 1 over 2. So now you know the point that we're talking about is 0 and 1 over 2. So we've got that point now. Right? So this is the point 0 and 1 over 2. That's one thing that we needed. Now we need the gradient of that tangent as well. We have dy over dx. What's dy over dx? We found that above. This was dy over dx, right? Two sine square t times cos square t. Now again, remember the actual form is this: 2 sine t whole squared into cos t whole squared. So we can input that value of t now that we found there, and this as well. What does that give us? 2 sine of 𝗑/4 whole squared times cos of 𝗑/4 whole squared. Put this on a calculator directly. See what you get from that. Has anyone done this? 2 into sine 𝗑/4, that's actually √2/2. I'll put that directly here. √2/2 whole squared. And then the other thing is also √2/2 whole squared, so I can put power 4 there. Okay, so if you do this, you will get 1/2 from this, okay? Put this on a calculator, you should get 1/2. No? 1/2, right? That's what you should get, 1/2. The gradient, yeah, okay. So the gradient of the curve turns out to be this. So we have a point, we have the gradient, and that point happens to be the y-intercept as well, right? The x coordinate is 0. So we can just use y equals mx plus c here. Y equals 1/2x plus the y-intercept. This is going to be c. So it's half x plus 1/2. That is going to be the equation of the tangent that we're looking for. This is a very common question, common type of question on implicit differentiation, that they make you find the derivative in the first part using parameter. Sorry, I said implicit by mistake. Parametric differentiation. It's a very common type of problem in parametric differentiation, that in the first part they will make you find the derivative using parametric differentiation, and then in the second part they would make you find equation of tangent. Okay, I hope that makes sense. If there are any questions, you can let me know. Otherwise, we're going to end this here. And now what you will do is, first of all, for tomorrow's class, make sure that you have completed the trigonometry worksheet, and maybe done more questions apart from the worksheet from recent papers as well, so that you know where you're having problems, and you can ask about them in tomorrow's class. Tomorrow is going to be trigonometry past paper practice day. And then when we come back on Monday, you'll have 3 days after tomorrow to do practice questions on differentiation worksheet as well, right? So you'll spend those 3 days and practice questions on this, and try to attempt all the questions apart from the ones that require you to do implicit differentiation. Now, what would that be? How would you figure that out? Whenever you see questions that do not have y as the subject, okay? So any questions in which they want you to find the derivative and y is not the subject, you can leave those questions for now, okay, where y is not the subject. But apart from that, you can attempt the rest of the questions from the worksheet. Please make sure to do that so that we can then have good questions to practice that you found difficult while you were attempting. If you have any questions, you can let me know now. Otherwise, you're free to leave. I'll see you again tomorrow, inshallah. Allah Hafiz. Yes, Ibrahim, please be quick though. Have you sent it to me? Okay. Complex numbers. इब्राहिम अभी सेंड किया आपने? Did you message directly or on the group? Okay. All right, so you're saying that the complex number W is defined this. In the first part, you showed this, and now the second part says it's given that P is a real number such that argument of W plus P is between pi over 4 and 3 pi over 4. Find a set of possible values of P. Okay, you see P is a real number, right? P is a real number. So what you've done already is that you've found tan of pi over 4. Can you explain what you've tried to do here?
देखो जो आर्ग्यूमेंट के अंदर लिखा हुआ है W प्लस पी उसके अंदर इनपुट किया तो मेरे पास रियल वाला पार्ट आ जाएगा P+2 और जो दूसरा पार्ट होगा कॉम्प्लेक्स वाला वो 4 आ गया तो फिर एक मेरे पास वैल्यू है मिनिमम tan पाई ओवर 4 और दूसरी मैक्सिमम है tan पाई 3 पाई ओवर 4
Yeah.
तो उनको इक्वेट किया विद 4 ओवर P+2 और फिर अनदर को 4 ओवर P+2 फिर उसको सॉल्व करके P की दो वैल्यूज निकाल ली
ठीक है. So if you've done this correctly, then you just have P just has to be between these two values, right? You have found two extreme values. One extreme value is -6 and the other extreme value is 2. So you just have to be between those two values. When you say you have to be between those two numbers, all that means is you write it in this form. You always write it in this form. With the less than signs, you write the smaller number on the left side, the larger number on the right side. It has to be between these two numbers because you found the two extreme cases, right? -6 and 2. So you just have to be between those two numbers.
जैसे जो बड़ा एंगल है उससे -6 आ रहा है और जो छोटा है उससे 2 आ रहा है
No, that does matter because remember the standard form is W Z minus something, right? So this would actually be W minus P. So that's why it's kind of reversing. It happens in range questions as well sometimes, right? So for example, if you remember trigonometric functions, if you have a function like this, y equals 2 minus sine of x, and you have to find the range of this function. If you input sine x equal to 1, that gives you y equal to 1. If you input sine x equals -1, the other extreme point, that gives you y equals -3. Sorry, y equals 3. So the smaller value is given you the bigger value, the larger value is given the smaller y value, but you still say that the range is between 1 and 3. It's just that the smaller value is giving you, the smaller argument is giving you the larger value of P, and the bigger is giving you the smaller value of P. It doesn't matter. You've just found the two extreme values. All you have to do is just say that the value of P is going to be between those two values. And when you say between two values, you always write the smaller number on the left, larger number on the right with less than signs like this. Okay? Part 3, what about that?
I didn't know. I plotted the points, but I didn't know how to do it.
Okay, the complex conjugate of W is W conjugate. The complex number is W and W conjugate represented by the points S and T. Find in terms of C minus A equals K. The equation is circuit passing through S, T, and the origin. Okay, so you have written, you have plotted those points. W is 2 plus 4 iota and the conjugate. Equation of the circle passing through S, T, and the origin. And they're saying that these points are S and T, right? So this point is S, this point is T, and there's origin. So you'll get a circle that looks like this, right? Roughly.
Yes.
Hmm?
Yes.
You have to write down the equation of the circle. Remember the standard form of equation of a circle and an Argand diagram? It's the same form that they've given here. In this form, A is the center and K is the radius. So you just have to find the center of the circle and the radius of the circle. Once you have those two things, you can write down the equation. Okay?
But how, sir?
Yeah, so that's the question now. Okay, center कैसे find करें और radius कैसे find करें? That's the problem. Okay, let's think about that now. So we have W and we have W conjugate. That's what you've done. You have 3 points on the circumference. The center has to be on the x-axis. That's for sure because that's a chord. It's going to be on the perpendicular bisector of that. But where exactly then? What did we do in the first part? These are real numbers. Second part, W plus P, that does not look like it's related. Okay. Achha, one way to think about this could be that you say, like we do in equation of circle in paper 1, you have this chord, right? Center of the circle has to be on the perpendicular bisector of this chord. So it has to be on the x-axis. Does that make sense? Because in a circle, center, perpendicular bisector of every single chord has to pass through the center of the circle, right? That's a property that we have, that we do in paper 1 generally. Coordinate geometry, equation of circle. It comes from this angle property of circle, that for any chord in a circle, if you were to draw a perpendicular bisector, it always will pass through the center of the circle. It comes from this property that a line drawn from the center of the circle to the midpoint of a chord, it makes a 90 degrees. Using that property, you basically have this result. Perpendicular bisector of every chord in a circle passes through the center of the circle. Okay? So if you have any two chords in a circle, this is the process that you can use to find the center of the circle. What you do is you find equation of one perpendicular bisector, find equation of the other perpendicular bisector, solve them simultaneously, and you get the equation of the, you get the coordinates of the center. Does this process make sense to you? Ibrahim, are you still there?
Yes, sir. I haven't seen this one.
Okay, so let me explain. You have a circle. If you have a chord in the circle,
All right, sir. I got it. Because it will pass through origin. We can solve it simultaneously, the both equations.
yeah, so that's one way of doing this. That's what I can think of in this right now. So basically, if you look at this now, this green chord is one possible chord that you can draw. Perpendicular bisector of this chord, it has to pass through the center. इसका perpendicular bisector क्या होगा? ऊपर 4 है, नीचे -4 है, तो वो यहाँ से जाएगा. It will be on the x-axis. So that tells you, okay, center has to be on the x-axis. Does that make sense? यहाँ तक clear है? Okay, now if the center has to be on the x-axis, एक चीज तो हमने figure out clearly. You can draw another chord now. You can draw this chord from origin to that point, right? Can you draw perpendicular bisector of this chord? इसका जो perpendicular bisector होगा, it will also pass through the center. It might look something like this.
Yes.
Although we can draw it very exactly in this case, because you remember how rotation works. If you're going 2 units right, 4 units up here, if we rotate at 90 degrees, it's going to be like this: 4 right and 2 down. It has to pass through this point. But if you want to do it by calculation, this is how it would work. You find the equation of the perpendicular bisector. You can do that, right? You can find the midpoint. The midpoint is 1 and 2, right? You can find the gradient of this line, original line. That's 4/2, that's 2. Gradient of perpendicular bisector will be -1/2. So what's the equation then? Y minus y1, y minus 2 equals -1/2 into x minus 1. Is that okay?
Yes, sir, I got it.
And now you can put y equal to 0 in this. And that
Fine.
gives you the x value, and that should be 5. Okay? That means this is the center. Center is at 5. What's the radius then? Radius is also 5. So equation is going to be like this: z minus 5 modulus equals 5.
जो हमने एसटी पे कॉर्ड बनाई थी, उस कॉर्ड की एक साइड हमें पता होगी कि एक साइड 4 है कि और दूसरी साइड 4 है, और जब बीच में से कट कर रहे हैं तो राइट एंगल भी बनेगा. तो उस तरह कैन वी डू दिस?
एक कॉर्ड से क्या पता है?
कि मतलब एसटी का पता है ना कि टोटल लेंथ कितनी है, 8 है इसकी. तो जब एस को बीच में से डिवाइड करेंगे और वो सेंटर पास करेगा तो वो भी 4 लेंथ होगा, ये भी 4 लेंथ होगी.
क्यों?
कॉर्ड जब बीच में से डिवाइड होती है सेंटर से, तो कॉर्ड का
अच्छा, ऊपर नीचे 4 होगा. Yes, that's correct. Oh yeah, so that might work as well. So you're saying if you draw this chord and then you make a triangle like this, right? Wherever the center is, we don't know what the value of that center is, right? But अगर हम randomly इसको mark कर लिया हमने, let's say, and now you're saying these two lengths have to be equal, right?
Yes.
And we know that this is 4 and this is also 4. What else do we know? और क्या बताएं यहाँ पे? एंगल चाहिए ना, कोई एंगल नहीं है.
हाँ जी, एंगल चाहिए.
अच्छा, let me just think of it another way. I think इस तरह से कुछ कर सकेंगे अगर हम यहाँ पे एक ये लाइन बनाएं. और ये दोनों रेडियस हो जाएंगे. We can say there's something like this here. Yeah, so we can make this triangle. इस triangle में देखें, this is radius, let's call that x. This is also radius, let's call this x as well. Okay?
Yes.
ये length पता है आपको, 2 and 4. So that will be square root of 20, right? This length.
Yep. Okay.
And you can find this angle as well. ये शायद आपने पहले पार्ट में कैलकुलेशन कहीं पे की हो, नहीं की, बट आप कर सकते हैं. You can find this angle, right? Tan inverse of 4/2, tan inverse of 2 basically. You can find that angle. लेकिन आपको एग्जैक्ट नहीं आएगा उससे. बट ओके, लेट्स ट्राई दैट. tan inverse of 2 ये कर लेते हैं. अब आपके पास ये एंगल भी है और आप साइन रूल लगा के कर सकते हैं.
आई थिंक आपको मेथड सही है. तो इसके अंदर तो
Oh, okay. So I found an easier way to open this now. Make this triangle. Make this triangle. It's a right angle triangle. Okay. If this length is x, we know this is 4.
Yes.
And we know this is going to be x minus 2.
Yeah. Yes. Yes.
ठीक है, जो भी टोटल होगा वो x होगा, उसमें से ये वाला 2 माइनस कर दें. And you can use Pythagoras now. You can say x squared plus 4 x squared plus x squared equals x minus 2 whole squared plus 4 squared, and that should give you the result x squared equals x squared minus 4x plus 4 plus 16, and 4x equals 20, x equals 5. Make sense?
Yes. सर लेकिन इससे तो सिर्फ वो आ रहा है ना, रेडियस आ रहा है ना इससे.
हाँ,
हाँ,
जब
रेडियस.
जब रेडियस
हाँ.
आ गया तो फिर सेंटर भी तो उतना ही होगा ना इधर इस
हाँ. हाँ, नहीं बोलती थी वो. ठीक हो गया सर.
ठीक है.
अल्लाह हाफिज.
ओके, अल्लाह हाफिज. M1 will start in the first week of March, inshallah. Both M1 and S1. All right, Allah Hafiz, everyone. I'll see you again in the next class then.